It is a world of profound silence, a stillness that is not peaceful, but heavy, final, and absolute. The wind does not whisper here, it pushes with the force of a deep ocean current, a slow, viscous sigh that has endured for eons. The light is a filtered, diffused gloom, a perpetual overcast twilight, where the sun is a faint, blurry stain behind a ceiling of perpetual poison. This is the surface of Venus, and upon a plain of cracked volcanic stone, a strange artifact rests. Its metallic form, now slowly surrendering to the corrosive embrace of the air, bears the markings of a civilization, of a species that once, with boundless ambition, reached across the void to touch this forbidden shore. This is the final space probe to ever land on the planet Venus. It is not merely a piece of machinery. It is a tombstone for an era of exploration, a monument to a specific kind of human audacity, forged in the crucible of ideological rivalry and cosmic curiosity. Its journey, and the saga of its mechanical siblings, represents one of the most extraordinarily brutal engineering challenges ever undertaken, a decades-long confrontation with a world that seemed to embody nature's most extreme and unforgiving principles. It is the last one in a long line of attempts made by the Soviet Union to explore the most dangerous place in our solar system, a program born of Cold War fervor and sustained by a stubborn, almost philosophical refusal to yield to the impossible. This is what they found when they landed on Venus, and in the quiet, corrosive death of this final lander, we find the complex answer to why they, and all who followed, never went back. The real mystery of Venus is not rooted in its obvious hostility, but in something far more profound and unsettling: how it can be so fundamentally similar to the Earth in its raw materials and birthright, and yet so catastrophically different in its destiny. They are siblings, born from the same stellar nursery, coalesced from the same swirling disk of dust and gas around our young sun. They are of comparable size, mass, and composition, so close that astronomers often refer to Venus as Earth's twin. Yet one became a cradle of water and life, of blue skies and temperate forests, while the other transformed into a pressure cooker of carbon dioxide, swathed in clouds of sulfuric acid, its surface hot enough to melt lead. This divergence is the central cosmic puzzle of our immediate neighborhood. It asks a question of existential gravity. Was Earth's path the inevitable one, or merely a fortunate roll of the celestial dice? Could Venus, under slightly different circumstances, have been our home, or does its hellish state represent a fate that our own world has narrowly, and perhaps only temporarily, avoided? To understand Venus is to hold a dark mirror up to our own planet, to see a potential timeline where the delicate balances that sustain us tipped irrevocably toward chaos, while Mars, with its rust-colored deserts and promise of ancient water, tends to capture the popular imagination and the bulk of contemporary exploration budgets in the 21st century. Back in the early feverish days of the space race, there was actually a more intense, more tantalizing focus on studying Venus. This initial preference was born of both ignorance and a specific kind of hope. Mars, even through the large Earth-based telescopes of the mid-20th century, was a relatively open book. Its thin atmosphere offered glimpses of a stark, cratered surface, of polar ice caps that waxed and waned with the seasons. The controversial canals, imagined by Percival Lowell, had been largely dispelled by clearer observations. What scientists saw was a quiet, cold, and seemingly static world. We already had a pretty good idea, a sobering suspicion, that there wasn't a whole lot going on over there, at least not on the surface. It was a distant desert, beautiful in its austerity, but unlikely to harbor the lush, teeming visions of alien life that fueled the public's imagination. Venus, on the other hand, has always been a master of concealment, a celestial sphinx wrapped in enigma. All that we could see from Earth, even with the most powerful optical instruments, was an impenetrable, brilliant cover of thick, unbroken clouds. These clouds, reflecting sunlight with a dazzling intensity that made Venus the brightest object in our sky after the sun and moon, were a perfect shield. They prohibited any glimpse of the terrain below, turning the planet into a featureless, glowing pearl. But in their very impenetrability, they whispered a secret. A world with such a dense, complete shroud could not possess a tenuous atmosphere like Mars. That luminous cloak meant the planet must be enveloped by a deep, substantial atmosphere, a gaseous envelope far more similar in substance to Earth's than to the near vacuum of the red planet. And here, basic orbital mechanics added a layer of tantalizing possibility. Venus orbits closer to the Sun than Earth, inside what we now term the inner edge of the habitable zone. Given its thick atmosphere, simple reasoning suggested it must be warmer down there, perhaps significantly warmer. In an era before the harsh realities of radiative balance and runaway greenhouse effects were fully quantified, this combination, Earth's size, a substantial atmosphere, and proximity to the Sun, captivated the imagination of those of us on Earth. It conjured visions not of a frozen wasteland, but of a primordial jungle. Our closest planetary relative, scientists and writers alike speculated, could be a lush tropical rainforest world, brimming with alien flora, a steamy environment where strange insects and reptiles might thrive in perpetual summer. It was a vision of a living, breathing twin, a carboniferous period on a planetary scale, a swampy paradise awaiting discovery. Now, even as late as 1960, this was still just a speculative theory, though one considered far more plausible than any contemporary vision of life on Mars. The scientific community was divided, a schism between the optimists, who saw potential for biology in the clouds or on a warm surface, and the growing number of atmospheric physicists who were beginning to piece together a much grimmer picture. The famous astronomer and astrophysicist Carl Sagan, then a young scientist, had already begun to popularize a more ominous and ultimately correct model. Using early spectroscopic data and principles of planetary thermodynamics, Sagan argued that the unbreaking cloud cover of Venus was likely not made of water vapor, but of other compounds. He postulated that this shroud was the result of a greenhouse effect that had gone wildly, catastrophically out of control. In this model, the very atmosphere that promised warmth had become a blanket too effective, trapping solar energy with such efficiency that it had superheated the entire planet, boiling away any ancient oceans and baking the surface into a sterile furnace. The world below the clouds, Sagan warned, would be nothing more than a scorched hellscape, a cautionary tale of planetary climate gone awry. But between the dream of a tropical twin and the nightmare of a pressurized oven, there was only one way to settle the debate. Speculation, whether optimistic or dire, would have to yield to data. The space race, which had begun as a contest of ballistic missiles and orbital firsts, was about to turn its engines toward the morning star. As with so many of the early headline-grabbing milestones in that race, the Soviet Union was the first to marshal its resources and aim for Venus. The year was 1961, a period of breathtaking momentum for the Soviet space program. They had already seized a dominating psychological and technological lead over the United States by hurling the first artificial satellite, Sputnik, into orbit in 1957, its simple radio beep-beep a shockwave heard around the world. Then, in April of 1961, they achieved the unimaginable by launching the first person, Yuri Gagarin, into space, his single orbit, a feat that redefined the human condition. They had even been the first to physically touch another world, albeit roughly, with Luna 2 impacting the Moon in 1959. The cosmos, it seemed, was speaking Russian, and since Venus, gleaming brightly in the dawn or dusk sky, was the next closest celestial object beyond the Moon, sending a probe there was an obvious, almost inevitable next step in this sequence of conquests. It was a target that offered both scientific prestige and the potent propaganda of another first. We must understand that at this nascent stage, these early interplanetary missions were not, in their primary conception, voyages of pure scientific discovery. The science was a secondary benefit, a valuable payload to justify the immense effort. The core driver was the act itself, being the first to achieve a historic milestone, to plant a metaphorical flag on a new frontier of engineering. If we learned some interesting facts about space along the way, that was excellent, but the overarching goals were geopolitical. Propaganda and political gains reigned supreme in the Cold War era. Every successful launch was proof of the superiority of a social and technological system, a demonstration of power aimed as much at Earth-bound allies and adversaries as at the stars. With their aim set clearly on adding Venus to a growing list of accomplishments, the Soviet engineers at the design bureau OKB-1, under the leadership of the legendary Sergei Korolev, built two nearly identical probes, Venera 1 and its backup Venera 2. This practice of launching in pairs was a pragmatic acknowledgement of the immense fragility of these early spacecraft. The technology was so new, the environment so poorly understood, that failure was not a possibility but a probability. Launch vehicles exploded, communications failed, power systems shorted out in the harshness of space. Sending twins doubled the odds that at least one might survive the perilous journey. One must pause to appreciate the sheer raw ambition of these first primitive attempts at interplanetary flight. Today, we are accustomed to spacecraft guided by autonomous computers, executing complex navigational corrections with atomic clock precision, communicating across billions of miles via the delicate ballet of the Deep Space Network. In 1961, the engineers had nothing more than the rudimentary computational power of early electronic calculators. Their guidance systems were basic. Their probes were simple pressurized containers of nitrogen or argon housing, primitive electronics, stabilized by spinning like a top. They strapped a small rocket engine to their probe for a mid-course correction, loaded the entire assembly on top of a modified ballistic missile called the R-7, the same workhorse that launched Sputnik and Gagarin, and after meticulous calculation of celestial mechanics, they set a course for Venus. Then they ignited the engines, let it rip, and hoped for the best. It was an act of faith as much as engineering. Venera 1 launched on February 12, 1961. For a time, it was a triumph. It became the first human-made object to be placed on a trajectory to another planet. But the cosmos is indifferent to firsts. En route, at a distance of about 7.5 million kilometers from Earth, the spacecraft's star tracker attitude control system failed, possibly due to overheating. The probe lost its orientation, its solar panels could no longer track the sun reliably, and the batteries drained. Contact was lost. Venera 2, launched shortly after, suffered a similar communications failure before reaching its target. The good news, gleaned from limited telemetry, was that both probes were able to fly within roughly 100,000 kilometers of Venus, proving the basic feasibility of the interplanetary trajectory. The bad news was definitive. Both experienced complete system failures before reaching their destination, and therefore no usable scientific data about Venus itself was returned. They were silent ghosts sailing past the shrouded world they were meant to unveil. While the Soviets retreated to their drawing boards to diagnose the failures, the American Space Agency, NASA, pressed forward with its own first attempt. Stung by the string of Soviet firsts, the United States was determined to demonstrate its own technical prowess. In 1962, NASA's Mariner 2 probe succeeded where the Soviet probes had faltered. It was a lighter, simpler spacecraft, focused on a flyby rather than a landing or atmospheric entry. After a trouble-plagued journey of its own, Mariner 2 sailed within 34,833 kilometers of Venus on December 14, 1962. For 42 minutes during its closest approach, its instruments scanned the planet. What it found was not a steamy jungle, but data that confirmed the darker theories. The microwave radiometer readings were startling. Temperatures measured in the clouds and inferred for the surface soared to approximately 900 degrees Fahrenheit or 480 degrees Celsius, far beyond the melting point of lead and double the boiling point of water at Earth's surface pressure. And that was just what could be measured from a distance. The data painted a picture of a global crushing greenhouse effect. Furthermore, Mariner 2 discovered that the cloud deck was incredibly deep, extending from about 60 to 80 kilometers above the surface. On Earth, such a structure would mean clouds stretching from the ground far beyond the stratosphere, a blanket of unimaginable thickness. And yet, even this immense shroud was not transparent. The surface of Venus remained shrouded in mystery, but the conclusion was inescapable. The surface environment was incompatible with life as we know it, or with the survival of any machinery then conceived. Based on this decisive data, NASA made a strategic calculation. The moon race was heating up, and Mars offered a more tractable, if cold, target. Venus, in the short term, was deemed an environment totally inhospitable for either man or machine, a scientific dead end of extreme difficulty. They would largely pass on further dedicated exploration of Venus for the time being, switching their focus to the lunar challenge and the ruddy plains of Mars. The Soviet reaction to Mariner's findings was characteristically different. Where NASA saw a dead end, Soviet scientists and engineers saw an unconquered summit. They were less convinced that the story was fully told. The data was from a flyby, from the outside looking in. What secrets lay within that atmosphere? What was the surface actually like? They felt, with a mix of national pride and scientific curiosity, that they were on the cusp of a monumental discovery, one that required not a distant glance, but a plunge into the abyss. And with the Americans seemingly bowing out of the immediate competition, the glory of being the first to penetrate the veil was theirs for the taking. They refocused their efforts with renewed determination, preparing for a second, more robust wave of Venera probes. These would not be mere flybys. They would be atmospheric entry probes designed to descend into the hellish unknown. But they had no idea, not truly, just how phenomenally bad, how physically oppressive things were about to get on the surface of Earth's twin. The year is 1966, and the landscape of the space race has transformed. The American Gemini program is mastering orbital rendezvous and spacewalks. The Apollo program is building the Saturn V rocket, a machine of pure ambition designed for a lunar landing. Landing people on the moon has become the singular, consuming priority for both superpowers. But this does not mean the Soviets have forgotten about Venus. In fact, they have spent the intervening 4 years learning from the failures of Venera 1 and 2, and from the American data to build a bigger, tougher, more sophisticated spacecraft. The new models, Venera 3 and 4, are substantial vehicles, weighing in at over 900 kilograms, a significant increase from the approximately 650 kilogram probes of the previous generation. They are equipped with a suite of instruments designed for in situ analysis, a barometer to measure atmospheric pressure, a radar altimeter to gauge height above the surface, gas analyzers to sniff the chemical composition of the air, thermometers to record the terrifying temperature gradient, and most crucially, a detachable spherical pod that would serve as a descent module. The concept was elegant in theory. The main bus spacecraft would fly by Venus, releasing the descent module on a trajectory to enter the atmosphere. The module, protected by a blunt heat shield, would plunge into the clouds, decelerate through aerodynamic braking, then deploy a parachute to drift slowly down through the layers of the atmosphere, taking readings of composition, temperature, and pressure all the way to the surface, radioing the data back to the flyby bus, which would then relay it to Earth. In reality, the complexity of interplanetary exploration in the 1960s meant things got complicated. Venera 3, launched in November 1965, experienced another critical systems failure during its cruise, likely a overheating similar to its predecessors, and fell silent. But Soviet celestial navigation was precise. The probe, a blind, silent cannonball, remained on its perfect trajectory. On March 1, 1966, it became the first human-made object to impact another planet, crashing into the night side of Venus. In a darkly comic historical footnote, the USSR had now achieved a hat trick of high-impact planetary exploration. They were the first to crash into the Moon, into Venus, and later they would be the first to crash into Mars. There is a lesson in there, perhaps. If you are going to fail, fail historically, fail in a way that still marks a boundary crossed. Venera 3 was a failure that nonetheless represented a milestone in reach. Venera 4, launched in June 1967, was the closest yet to a definitive success. The probe made the interplanetary journey intact, with all systems operational. On October 18, 1967, it released its descent capsule, which pierced the Venetian atmosphere at a staggering speed. The heat shield glowed with the fury of re-entry, protecting the precious sphere within. The parachutes deployed, and for the first time in history, a spacecraft from Earth began a controlled descent through the alien skies of another world. This was a monumental moment, the first direct measurement of conditions within the atmosphere of a planet beyond our own. The data that streamed back, first to the flyby bus and then across tens of millions of miles of space to eagerly waiting Soviet scientists, was revelatory and terrifying. It confirmed Mariner 2's findings and added frightening new dimensions. At high altitudes, around 55 kilometers above the surface, the atmosphere of Venus was surprisingly, deceptively benign. The temperature was a comfortable 30 degrees Celsius, the pressure only a fraction of Earth's surface pressure. It was, as one scientist noted, akin to a warm summer day on Earth, a perfectly hospitable environment for machinery, and in the fevered speculation of the time, perhaps even for some form of floating cloud-borne life. But this was a cruel illusion, a thin, habitable band in a sky of poison. As the probe descended further, the measurements began to climb. Not just the temperature, rising steadily, but the atmospheric pressure increased exponentially. The scientists watched the numbers on their consoles climb into realms that defied terrestrial experience. It was akin to diving deep into an ocean, but an ocean made of gas. The very air was becoming not just thick, but crushingly heavy. The transmissions told the story of a world where the environment itself was an active, violent force. After approximately 93 minutes of descent, the signals from Venera 4 stopped abruptly. The probe had been designed to withstand pressures up to 20 atmospheres. The last data point it returned indicated an external pressure of 22 atmospheres, and the temperature had soared to 2062 degrees Celsius. It is widely believed that the spherical capsule, a masterpiece of engineering for its time, was simply crushed like a tin can by the incomprehensible weight of the Venusian atmosphere long before it ever reached the ground. The surface, it was now clear, was even more extreme. Armed with this new, harrowing information, the Soviet engineers knew with near certainty that their next planned probes, Venera 5 and 6, which were of the same basic design as Venera 4, had no realistic chance of surviving all the way to the surface intact. Their pressure vessels were not strong enough, but they launched them anyway in January of 1969 in a pair of back-to-back missions. Why send them to almost certain destruction? The answer lies in the shifting tides of the space race. By 1969, the Americans were on the cusp of the ultimate prize. Apollo 8 had already flown a crew around the moon at Christmas 1968, sending back the iconic Earthrise photograph. Apollo 9 and 10 were testing the lunar module in Earth and lunar orbit. The first human steps on the lunar surface were imminent, scheduled for that summer. The Soviets knew internally that their own rival lunar landing program, the N-1 rocket, was plagued with problems. They were not going to be able to match the American achievement. But perhaps, if their Venus exploration could yield a stunning first, a direct measurement from the surface, a photograph, they might still salvage a position of leadership in robotic interplanetary exploration, a field where they could still claim supremacy. It was a strategic pivot, a way to remain competitive in the grand narrative of the space race, even as the lunar chapter closed for them. Success, however, would not come easily. Venera 5 and 6 performed their missions dutifully. They entered the atmosphere on May 16 and 17, 1969, respectively, and parachuted downward, transmitting valuable data about the atmospheric structure and composition. They confirmed the immense pressures and temperatures, but as predicted, they were not survivors. Venera 5 transmitted for 53 minutes before falling silent at an altitude of about 24 kilometers, crushed by a pressure of 27 atmospheres. Venera 6 lasted 51 minutes, succumbing at a similar altitude under 27 atmospheres of pressure. They had been designed for 25 atmospheres. The reality was even harsher than their hardened shells could bear. Once again, the surface remained untouched, a realm just out of reach, protected by an ocean of supercritical carbon dioxide. And yet, the Soviet Union was not discouraged. Defeat in this context was merely data. Each failure taught them what the environment demanded. The answer was not to abandon the attempt, but to build bigger, stronger, more resilient probes. They would try again, but this time, they would design for the inferno they now knew awaited. For their next attempt, Venera 7 and 8, the engineers at the Lavochkin Design Bureau, which had taken over planetary missions, made two fundamental modifications to the descent module. First, the outer pressure vessel was constructed from thicker, stronger steel, designed to withstand not 20 or 25 atmospheres, but an estimated 180 atmospheres. Second, inside this outer shell, they placed an inner sphere made of titanium, the strong, lightweight metal used in high-performance aircraft. This titanium sphere would house the actual electronics and instruments, providing a second line of defense against heat and pressure. The space between the outer shell and the inner sphere was filled with a dense fibrous insulation material, not only for thermal protection, but also to act as a shock-absorbing cushion for the final impact. Because after analyzing the data from Venera 4, 5, and 6, the Soviets made another critical realization: the parachutes were a liability. In the deep, dense lower atmosphere, They were not just slow, they kept the probe suspended in the extreme heat and pressure for too long, increasing the risk of systems failure before touchdown. The new plan was more brutal, more direct. Use a parachute only for the initial deceleration in the upper atmosphere, then jettison it and let the probe fall freely, using the incredible atmospheric density itself as a braking mechanism. It was a calculated gamble. On August 17, 1970, Venera 7's descent module entered the atmosphere of Venus. The sequence began nominally. The heat shield ablated away. The parachute deployed. But then, as feared, something went wrong. Either the parachute material, likely degraded by the sulfuric acid clouds and heat, ripped, or its lines melted or snapped. The lander began to fall rapidly, tumbling, reaching a terminal velocity estimated at 61 kilometers per hour. It struck the surface with a hard impact. The telemetry signal, monitored by scientists half a world away, became weak and garbled. For 23 minutes, they listened to what seemed like noise. The initial assumption was another failure, a probe shattered on the rocks of Venus. But Soviet technicians, with dogged persistence, spent weeks analyzing the faint signal tapes. Buried in the static was data. The probe had survived the impact. Its main antenna was damaged, likely bent or broken, but a smaller omnidirectional antenna was still transmitting weakly. Venera 7 had become the first human-made object to land on another planet and transmit data from its surface, and what it reported confirmed the very worst fears, pushing the known limits of habitability into a new realm of extremity. The temperature at the landing site was measured at 475 degrees Celsius, roughly 887 degrees Fahrenheit, hotter than the inside of a wood-fired pizza oven, hot enough to make zinc flow like water. The atmospheric pressure was a crushing 92 times that of Earth at sea level, equivalent to the pressure found nearly 1 kilometer beneath the ocean's surface. It was an environment where not a single component of the probe was operating within its designed parameters. Every resistor, every capacitor, every transistor was being pushed far beyond its rated limits. That it functioned at all, even briefly, was a minor miracle of engineering overkill. And yet, the Soviets were undeterred. At this point, having come so far, what did they have to lose? The Americans had already planted their flag on the moon in July 1969. That symbolic race was decisively won. But the Soviets were left with other frontiers to conquer, other firsts to claim. They could be the first to make sustained, game-changing discoveries on the surface of another planet. They could be the first to land on Mars. This became the new strategic direction for the Soviet space program in the 1970s, a pivot toward ambitious robotic interplanetary exploration, a domain where they could still excel and lead. In 1971, they launched Mars 3, which achieved the first ever soft touchdown on the surface of the red planet. The lander operated for a mere 20 seconds before succumbing to a planet-wide dust storm, but it was, again, a historic first. Then, in 1972, they returned to Venus with Venera 8. This time, fortune smiled. The probe experienced no major technical difficulties. The descent module parachuted down smoothly, its chute crucially functioning correctly, and made a soft landing on the day side of the planet. It operated for 50 minutes on the surface, transmitting a wealth of data. It confirmed the hellish figures from Venera 7 with precision and added new, critical details. It measured the light levels at the surface, finding that despite the perpetual global cloud cover, the illumination was similar to a heavily overcast day on Earth, enough to see, enough perhaps to take a photograph. It also analyzed the surface composition with a gamma-ray spectrometer, finding levels of radioactive potassium, uranium, and thorium similar to terrestrial granitic rocks. But most significantly, it confirmed the presence of fierce winds and provided the first direct evidence that the lower atmosphere was not just hot and dense, but chemically hostile, laden with corrosive agents. By now, the portrait of Venus was horrifically complete. In addition to the extreme temperature, hot enough to melt lead and zinc, the air pressure on the surface was the equivalent of 92 Earth atmospheres, a force that would instantly crush any conventional submarine not designed for the abyssal depths. And if the heat and pressure were not enough, the atmosphere itself was a toxic brew. The clouds, it was confirmed, were composed primarily of sulfuric acid droplets, the same highly corrosive acid found in car batteries. This rain of acid, however, never reaches the surface as a liquid. The extreme heat evaporates it into a mist long before it could fall, creating a superheated, corrosive haze in the lower atmosphere. You would think that this accumulated confirmed knowledge, this litany of existential threats, would finally deter even the most die-hard engineers and funding committees. The surface of Venus was not just hostile, it was an archetype of hostility, a benchmark against which all other harsh environments in the solar system would be measured. But the Soviet Union, in this era, did not believe in quitting, not when they were this close to cementing a legacy as the first and only interplanetary explorers to touch this forbidden world. The very difficulty became the attraction, and Venera 8 had revealed one final, tantalizing fact. There was enough light. If they could build a probe robust enough to survive the descent and the initial moments on the surface, and if they could protect a camera system during the fiery entry and corrosive descent, they could open humanity's eyes to the surface of another planet for the very first time. No artist's impression, no radar map, but an actual photograph from the ground for a propaganda apparatus and a scientific community fueled by firsts. This was a goal of incalculable value. So they aimed their sights once more directly at Venus. For Venera 9, the Soviets made a fundamental and radical change to the probe's design, and you can see the evolution just by looking at it. The entire spacecraft was a behemoth, reflecting years of accumulated experience and a brute force philosophy. The descent capsule itself had been beefed up yet again, now part of a spacecraft assembly, tipping the scales at nearly 5 metric tons at launch, around the weight of a fully grown African elephant hurled into interplanetary space. But the standout features were those born of harsh lessons. Given everything they now knew, the goal was to minimize the probe's exposure to the extreme environment. The long, slow parachute descent was a liability. They had also learned from the accident of Venera 7 that even a probe dropped like a rock could survive the impact if properly cushioned. So they asked a revolutionary question: what if we designed for that? What if we intentionally dropped the probe, using the atmosphere itself as the primary brake? This philosophy is embodied in those 2 distinctive rings visible on the Venera 914 landers. At the bottom is the landing gear, or more accurately, the impact ring, a flat circular metal skirt connected to the main body by a series of compressible shock-absorbing legs. It is not designed for a gentle setting down. It is designed to smack into the ground and distribute the force. At the top of the lander is a new aerodynamic brake, a blunt, dish-shaped structure. This is how they landed on Venus, with no final stage parachute required. This weird hat, as it appears, is all that is needed to slow the probe's free fall through the lower atmosphere to a survivable speed. It works because the incredibly thick atmosphere of Venus, with its pressure 92 times Earth's, behaves less like a thin gas and more like a viscous fluid, like water or syrup. The aerodynamic brake creates immense drag, turning the kinetic energy of the fall into heat that is dissipated into the surrounding atmosphere. The entire descent sequence became a precisely choreographed ballet of violence. Enter at interplanetary speed, behind a heat shield, deploy a small pilot chute to stabilize and slow the initial descent, then jettison the parachute and the upper aerobrake cover, exposing the main dish-shaped brake. Then fall. For the last several kilometers, the lander would plunge through the orange gloom, its speed bleeding away until it struck the ground at roughly 25 kilometers per hour, a hard but survivable impact. And then the cameras, protected behind dense pressure-resistant quartz windows and sealed behind a pyrotechnically released lens cap until the last possible moment. They were the heart of the mission. On October 27, 1975, Venera 9 touched down on a rocky slope. The lens cap was ejected, and for the first time in the history of life on Earth, eyes, mechanical, human-made eyes, opened on the surface of another planet. This is the first photograph ever taken of the Venusian surface. It is a stark, grainy black and white image of profound significance. What we are looking at is a field of broken, jagged, sharp-edged rocks, some as large as half a meter across, scattered across a background of finer sand-like material. There is no dust, no smooth erosion as we see on Mars. The rocks are angular, fresh-looking. The horizon is visible, curving slightly at the edge of the 180-degree panoramic scan. The sky is a featureless bright gray. It is not exactly breathtaking in its beauty. Its power is purely ontological. It is there. It is real. The vision of a swampy jungle is annihilated forever, replaced by a desolate burning scree slope. It is interesting precisely because it was taken on Venus, because it represents the end of millennia of speculation and the beginning of direct knowledge. It is, in its grim simplicity, very cool. Venera 10, an identical lander, arrived just 3 days later and touched down about 2,200 kilometers away. Its photograph revealed a different, but equally telling vista. Here, the view is of a flat plain, strewn with pancake-like smooth rocks, with weathered edges, sitting atop what appears to be a granular surface. Scientists interpreted this as the top of an ancient, weathered lava flow, a geological snapshot of a world whose surface had been repeatedly resurfaced by global volcanic activity. The twin images immediately suggested a geologically active, complex world, not a monotonous desert. Venera 11 and 12, launched in 1978, were more focused on atmospheric and chemical analysis. They were less eventful in terms of public spectacle, as both suffered failures with their camera lens cap deployment systems. One of the cruel tricks of Venus exploration was this: you had to protect the delicate camera optics during the fiery entry and corrosive descent with a robust sealed cap. But then you had to rely on a small explosive charge or a mechanical actuator to remove that cap after landing. In the extreme heat, these mechanisms could fail. The explosives could degrade, the actuators could seize. Both Venera 11 and 12 landed successfully and returned a wealth of data on atmospheric composition, lightning, and surface chemistry, but their eyes remained closed. They sent back only data, no images. Then came Venera 13, an unlucky number in some traditions, but for the Soviet Venus program, it represented the pinnacle of its engineering and scientific achievement. Launched in 1981, it was a masterpiece of hardened robotics. On March 4th, 1982, it touched down in a region known as the Phoebe Regio, and it performed flawlessly. It returned the first ever color photographs of the Venusian surface. The images, processed from separate red, green, and blue filters, reveal a landscape that is both familiar and utterly alien. The surface around the lander is a flat plain of yellowish-brown, slab-like rocks, reminiscent of cracked mud or layered sedimentary rock, but they are almost certainly volcanic in origin. The color is thought to be a result of the scattering of sunlight through the thick sulfur-laden atmosphere, filtering out the blue light and casting everything in hues of orange, brown, and yellow. But the true awe in the Venera 13 panorama comes from the context. The probe had landed near the edge of a low outcrop. In the color image, you can see the base of the lander, its apparatus, and then stretching into the distance, a layered rocky landscape that provides a genuine sense of depth and scale. It makes the scene seem more real and simultaneously more alien. This is not a studio mock-up, this is a place. The sky is a dull yellowish gray, a perpetual suffocating overcast. You can also see in the image the distinctive teeth on the base of the lander's impact ring. These brutalist-looking metal fins were not decorative. They served a critical aerodynamic function. Added after earlier probes experienced unstable spinning descents, these fins acted as stabilizers, preventing the lander from rotating or shaking violently as it fell through the turbulent lower atmosphere, ensuring a more controlled and upright final impact. But Venera 13 was more than a camera. It was a complete geological laboratory. The probe was equipped with a drill and a surface sampler arm. Using a motorized drill, it bored a small core into the Venusian soil, retrieved a sample, and placed it inside a sealed chamber within the lander for X-ray fluorescence analysis. What it found was a material chemically very similar to a terrestrial rock we call tuff, essentially solidified volcanic ash. This was direct physical evidence of volcanism, of the fiery processes that have shaped the Venusian surface. And then there was the sound. Venera 13 carried a microphone, a simple, ruggedized acoustic sensor. For a few minutes, it recorded the ambient sounds of Venus. What we hear is mostly the noise of the lander itself, the whirring of its mechanisms, the clunk of the drill arm. But beneath that, there is the low, constant roar of wind, a deep, powerful sigh as the supercritical atmosphere moves past the stationary probe. It is not the whistle of a terrestrial breeze, but the groan of a fluid under immense pressure and heat, flowing over an obstacle. Like the photographs, the sound is strangely mundane and profoundly alien simultaneously. It is the noise of another world. Venera 14, its twin, landed 4 days later and about 1,000 kilometers away. Its mission was similarly successful, returning another set of color panoramas and conducting soil analysis. Its images showed another flat plain of these smooth, pancake-like rocks, which subsequent analysis determined were chemically very similar to tholeiitic basalt, a common volcanic rock that makes up most of the Earth's ocean floor. The consistency of the findings was telling. Venus, it appeared, was a world dominated by volcanism, its surface a young geologically refreshed plain of igneous rock with little evidence of the water-driven erosion or plate tectonics that sculpt Earth. And then it stopped. Venera 14 was the last successful landing. Subsequent Soviet missions, like the ambitious Vega probes of 1984, which combined a Venus lander with a Halley's Comet flyby, delivered landers, but they were simpler, designed for atmospheric balloon experiments, and their surface operations were brief and yielded no new imagery. The final photographs from Venera 13 and 14 were, and remain to this day, the last direct visual glimpses humanity has had of the surface of Venus. That final space probe, its mission complete, now sits silently in the everlasting twilight, its metal slowly reacting with the corrosive atmosphere, its instruments long since cooked into inertness. It is a monument to a concluded campaign. Along with it comes the last photograph ever taken of the surface, a view that has not been refreshed for over 4 decades. But what we must dwell on, What is more significant than the technological triumph itself is the profound question of why we never went back. Why has this world so close, so similar in bulk to our own, been left to its solitude after such a costly and hard-won initial reconnaissance? The answer is not singular, but a confluence of realities, scientific, economic, and philosophical. One very obvious reason is the sheer disproportionate difficulty and expense for the scientific return. Venus is a master of destruction. You can send a sophisticated solar-powered rover to Mars like Spirit, Opportunity, or Curiosity, and it will operate for years, even decades, traversing kilometers of terrain, conducting thousands of experiments, returning terabytes of data. The longest any Venera lander ever survived on the surface was approximately 2 hours. Venera 13 lasted 127 minutes. The missions were sprints of frantic data acquisition against an inevitable rapid death by overheating. Every component had to be massively over-engineered, hermetically sealed, and pumped with coolant or insulated to a degree that made the spacecraft immensely heavy and complex. The cost per minute of surface operation was astronomically high. Once the initial fundamental questions, what does it look like? What is the temperature and pressure? What is the soil made of? Were answered, the justification for sending ever more complex and expensive short-lived landers became difficult to articulate. What more could you learn in 2 hours that would justify the hundreds of millions of dollars and years of development? Furthermore, the Venus program came to an end precisely as the political entity that birthed it was dissolving. The Soviet Union itself was coming to an end in the late 1980s and early 1990s. The economic turmoil that followed the collapse meant that the funding and institutional will for such audacious, high-risk interplanetary missions evaporated. Leadership and priorities changed fundamentally. The new Russian Federation struggled to maintain its existing space infrastructure, like the Mir space station. Ambitious new planetary missions were a luxury of a bygone era. The engineers who designed the Veneras retired or passed away. The institutional knowledge, while preserved, was not acted upon. Meanwhile, NASA, the other spacefaring power with the capability to mount such a mission, has largely been too sensible, too driven by a different scientific and political calculus, to attempt a direct assault on the Venusian surface in the post-Apollo era. The agency's strategy has been shaped by the faster, better, cheaper mantra at times, and by flagship missions at others, but always with an eye on maximizing scientific return and public engagement. Venus surface missions are neither fast nor cheap, and their returns, while profound, are not easily sustained. Trying to justify that cost to politicians and the public when you get so little operational lifetime in return is not an argument scientists would easily win, especially when competing against missions to Mars, the outer planets, or space telescopes that promise years of continuous discovery. NASA and other space agencies have focused instead on orbital reconnaissance of Venus missions like Magellan, which radar mapped 98% of the surface in the 1990s, or Venus Express and Akatsuki, which studied the atmosphere and climate from orbit. These missions are vastly less risky and expensive, and they provide global synoptic data that a single lander cannot. The surface remains the final, formidable frontier. So, for now, and for the foreseeable future, the surface of Venus remains one of the solar system's greatest and most frustrating mysteries. It is a world we have touched but not tamed, seen but not understood. We possess a handful of grainy photographs, a few minutes of audio, some soil samples analyzed in situ, but these are mere fragments of a vast global story. What is the detailed geological history recorded in those volcanic plains? Are there active volcanoes today, spewing fresh lava into that pressurized atmosphere? Could there be, in the high, cooler clouds where the pressure and temperature are nearly Earth-like, a niche for exotic, acid-tolerant microbial life? A last, tenuous holdout from a more temperate past? These questions linger, unanswered. The silence that has followed the Venera missions is not just a pause, it is a testament to the scale of the challenge. Venus is not merely a distant point of light or a fuzzy disk in a telescope. It is a real place, a physical environment of such overwhelming extremity that it defies our standard approaches to exploration. It asks not for incremental improvement, but for a quantum leap in materials science, in high-temperature electronics, in autonomous robotics. Some concepts for future missions imagine landers built from advanced ceramics and sapphire, with electronics based on silicon carbide that can operate at 500 degrees Celsius, or even more radical ideas, landers that are refrigerated, carrying their own brief pocket of coolness to the surface, or steampunk mechanical rovers operated by clockwork and springs, immune to the heat that fries semiconductors. But these remain concepts, dreams on drawing boards. The legacy of those Soviet landers, therefore, is multifaceted. They were instruments of Cold War propaganda, yes, but they transcended that origin. They were acts of extraordinary engineering courage, sending delicate machines into a known furnace. They were the vanguards of knowledge, replacing fantasy with hard, if grim, fact. And they stand as a permanent reminder of the duality of our cosmic neighborhood. In Venus, we see not just another planet, but a possible version of Earth itself, a road not taken, or a road we might yet stumble upon. The runaway greenhouse effect that scorched Venus is in principle no different from the warming processes we are initiating on our own world, albeit on a vastly different scale and time frame. Venus is the ultimate climate change parable, a planet where the feedback loops ran away completely, leaving a world desiccated and superheated. As we look up at the evening star, shining with a serene, steady light, we now know the truth that lies beneath that brilliant cloud deck. It is a truth of crushing pressure, corrosive chemistry, and blistering heat. It is a truth revealed by the courage and ingenuity of a generation of explorers who dared to send their mechanical emissaries into the abyss. Those last photographs, those fragments of data, are messages in a bottle from a shore we may not visit again for a very long time. They tell us that the universe is not obliged to be hospitable, that paradise is not a default setting, and that the conditions for life as we know it are terrifyingly fragile. The final space probe on Venus is more than a relic. It is a question etched in metal, posed to the future. Having learned the ferocity of this twin world, do we turn away, or does the very extremity of the challenge become the reason to return, armed with new tools and a deeper need to understand our place in this cosmic drama? For now, the question hangs in the thick, hot air, unanswered, while the probe slowly becomes one with the planet it was built to conquer. The mystery endures, so close, yet still so very far.